Okay, welcome back. This is Calc 2, Chapter 9, and if you're like me, you're going to see Chapter 9, and it's going to blow your mind. It's like, what is this all about? Where does it come from? Why does this not fit in my education one bit whatsoever? My argument is that it does, and it's a natural fit, and it's something we've kind of swept under the rug, and it's unfortunate. Okay, so this chapter is about the relationship between things like e to the x and these other things which are called Mclaren Series. Okay, so e to the x we'll find out is equal to 1 plus x plus x squared all over 2 plus x cubed all over 3 factorial plus x to the 4th all over 4 factorial, and on and on and on. Okay. Okay, so the deal is this thing on the right is kind of like a polynomial, but it's an infinitely long polynomial. Okay, so it turns out that it's kind of like the limit of a polynomial. It's a limit of a bunch of polynomials, basically, to get this. So that's what Chapter 9 is pretty much about. It's about connecting these weird kind of functions they throw on your lap after you learn about polynomials to polynomials. And I claim it's a natural kind of progression, which in a lot of ways mirrors your education. Okay, so people complain a lot about math education. I'm here to say that there was a genius behind the madness, okay? A madness to the genius or something, genius to the madness. I don't know, whatever. Okay, so what I'd like to do is take us back in time and talk about where we started with our education, okay, with natural numbers, right? So the natural numbers, I'll just put N for natural, are numbers like the counting numbers, the things you could do on your hand, like our caveman ancestors were definitely probably able to worry about numbers like these, right? Okay, then comes what? Well, we can add the number 0 in there, and then we get the whole numbers. Okay, so the whole numbers are the natural numbers, but we also get the number 0. Okay. And then one step further out, we end up with the integers, which they give the letter Z because of the German word for integers. Okay, and the integers are the whole numbers, the natural numbers, but then also the negative numbers. Okay. Then after you get a little further out, you get what are called the rational numbers, which I'll give the letter Q for whatever reason. Okay? And the rational numbers are basically the integers, the whole numbers, the natural numbers, but then you also get fractions, right? And terminating decimals. Okay. Then there's to the side here, there's the evil cousins, the irrationals. I'll just put these over here, which are numbers like e, pi, root 2, and any prime number square rooted. Okay. In order to kind of make my exploration work, I need to introduce this phrase, this word called closure, or closed, being closed. Being closed means that if I take two numbers from a particular group of numbers and I do some operation on them, I'm going to get the same type of number back. Okay, so some examples are probably the best way to explain what being closed is. The natural numbers are closed under addition. Okay, so for example, and I'm sorry about my writing, nature, jeez, man, natural numbers are closed under addition. So an example of that, I'm not going to prove it, but if you have 3 plus 2, so both of these are counting numbers. If you add those together, you get 5, which is another counting number. Okay. The natural numbers are not closed under addition. Or subtraction, rather. So, for example, you could take 5 minus 5, you get 0, which is a whole number, which is not a natural number, right? So, what about the whole numbers then? Are the whole numbers closed? Well, they're closed under addition, but they're not closed under subtraction either. Okay, so for example, if you take 5 minus 7, you'll get negative 2, which is not a whole number. The whole numbers are the natural numbers plus 0. Okay, this is negative 2 is not a whole number. So that's an integer. So what's happening is you kind of can move out one layer by using a particular operation. So I can get from the naturals to the whole numbers using subtraction. I'm going to put this in a different color. Okay, so using subtraction. Then I can get from the whole numbers to the integers. I can also use subtraction, right? So but I could also go from the naturals to integers using subtraction. Then once I'm in the integers are closed with regards to addition and subtraction. Okay. Let me just write addition and subtraction like that. Okay, I'll put them in parentheses. What about multiplication? Are the integers closed under multiplication? Well, yeah, it turns out, yeah. If you multiply any two integers together, you're just going to get another integer. So we can kind of expand that to include plus, minus, and multiplying. Okay. The same is true for the naturals and the whole. Those seem closed under multiplication as well. The only thing that's really jumping from one set of numbers to a new set of numbers is subtraction. Okay. But even subtraction won't screw you up once you get into the integers, right? You can subtract any two integers and you're just going to end up with another integer. So integers, so are they ever not closed? And I say yes, integers are not closed under division. For example, if you take negative 3 and divide it by negative 7, right, you're going to get what? You'll get 3 over 7, which is not an integer. It's actually a rational number, right? So we can jump out of the integers into rational numbers, but we have to use division. Okay. So I can jump out there using division. You can also jump out of the whole numbers using division. You can't divide by 0, but if you have like 5 divided by 3, you'll end up jumping out into the rationals. And likewise with the natural numbers, if you have like 2 divided by 5, again, you're going to jump out into the rationals. Okay. Once you're in the rationals, though, they're kind of closed, right? So once we get there, the rationals seem closed under everything. Okay. This is like no matter what you do with a rational number, you kind of end up with a rational number. So the question then becomes: doesn't it make sense if you could do all this other stuff? Why can't you kind of jump from rationals to irrationals somehow? Okay. Is there any operation that will allow us to operate on rationals to create an irrational? Well, yeah, you could see it right there. This weird square root thing. But there's other ones, and what I claim is it's this idea of taking a limit. Okay, so limits will allow you to jump out from the rationals into the irrationals. Okay. So rationals won't be closed under that limit process. Okay, so let's remind ourselves what a limit was, because we've used limits we've kind of abused them with the real numbers. We're kind of already working in the real numbers. We don't worry about the rationals or just working in the integers. There's other classes for that. If you take number theory, you'll learn about that. So the rationals, are not necessarily what we're used to doing limits with, but the idea of a limit in the context of a rational is you're looking at a sequence of numbers and kind of trying to figure out where the sequence goes. I mean, it's the same idea as what you kind of did in the real numbers with limits. So for example, if you had the limit as x goes to infinity of 1 over x, you could think of it as a sequence, right? So the x values are going to infinity. You go 10, 100, 1,000, 10,000. And 1 over x is what? Well, that's 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000. So the corresponding sequence to the limit is this sequence of numbers 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000. And then the limit of this thing is basically just asking, where does this sequence go? Where does it seem like this sequence goes? Well, it goes to 0. Okay. Okay. So here we have a sequence of rational numbers, which is going to another rational number, right? So this sequence looks like it's going to 0. These are all rationals, and this is a rational. But I claim that you can jump out of the rational numbers with these limits, with these sequences. So you can produce a sequence of rational numbers that actually goes to something that's not rational. In other words, the rational numbers are not closed with regards to limits, right? So I note then the rationals are not closed with regards to limits because there are situations like the following. The sequence of rational numbers 1, 1 plus 1/2, 1 plus 1, which is 2. Okay. 1 plus 1 plus 1/2. So my sequence, let me write it in a different way. It might be a little more pleasing. So up here when I wrote my sequences, we'll talk about the notation here in a bit. But this is A1. This is going to call it A2, the second term of the sequence. This is A3. This is A4, the fourth term of the sequence. Okay. Okay, so my first term of my new sequence of rational numbers, which I claim go to irrational number, my first number I claim is 1. And then my second number is going to be 1 plus 1. Okay. My third number is going to be 1 plus 1 plus 1/2. Okay. My fourth number is going to be 1 plus 1 plus 1/2 plus 1/6. My fifth number is going to be 1 plus 1 plus 1/2 plus 1/6 plus 1 all over 24. My sixth number is going to be 1 plus, well, it's A5, right? 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1 over 120. Okay? So let's see what those numbers are, right? What is the sequence of numbers? So we get 1. Well, clearly 1 is just 1. So let me write these out. 1, and then we get 2, and then we get 2.5, and then we get the next number in my sequence, 2.5 plus 1/6 is 2.6 repeating. And then we get which you can write as a fraction. So these are still rational numbers. Just because it's repeating like that doesn't mean it's irrational. If you want the rational form, 2.5 plus 1/6. Great. they're not going to give me the rational. So let's just go 1 plus 1 plus 1 plus 1 plus 1/2 is 8/3. So if you'd rather, this next guy then is 8/3. And then let me put the decimal in there as well. I want to cut to the punchline here. So 8/3 is, yeah, that's the 2.6 repeating. And then the next one, 6 plus 1 all over 24 is 65/24. As a decimal, that's 2.708 with a 3 repeating, I believe. And then plus 1 over 120 is 163 over 60, which is 2.716 repeating. Okay. And I claim that if you kept going in this process, and you can see a pattern, right? There's a definite pattern here. The pattern is you're always going, so a sub n will be 1 plus 1 plus 1 all over 2 factorial plus 1 all over 3 factorial. And you can look up what factorials are online. I'm not going to, we'll have to deal with factorials. Plus 1 all over, the last one will be n minus 1 factorial. Okay. So with a sub 5, the last one is 4 factorial. Yeah, so we'll deal with factorials here in this chapter. 3 factorial is 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, so this was 3 factorial. This is 4 factorial. This is 5 factorial. So there's a pattern there, right? And you can continue this pattern on indefinitely. Note all of these numbers on in our limit. In other words, in our sequence, are rational numbers, right? But I claim that where they're going is not an irrational number. In particular, it's actually the number e. So if you go to your calculator and already have it kind of typed in, you press the number e, what do you get? You get 2.71828. And you know, we're already pretty close to that, 2.716. This is 2.718. Okay, so it seems that if you take the limit of the sequence of numbers as you go to infinity, you're getting this number which is not rational. You found a way to jump from these rational numbers into the land of irrationals. Just like before, we used subtraction to go from naturals to integers, and before that you could use division to go from naturals to rationals. Now we've kind of found a way to tunnel from rationals to irrationals, and the operation that does it is the limit. Okay. So my objective here in this chapter 9 is to make this connection between e to the x and this sum. And I claim that it's the same thing here, except instead of using numbers, you just use variables instead. Okay? You just use polynomials. So you can kind of imagine your education with regards to functions, right? So first you were just dealing with numbers. We'll just stick with the rational numbers, right? So the Q numbers, 1, -2, 1/2, 3/4. And then they started teaching you about variables, so you can include polynomials. Okay? You can say, okay, 1 plus x, x squared plus 2x plus 1. So we got some polynomials hanging out in here. X plus 3, x cubed, or whatever. And then you can make rational equations from that. You know, the 1 all over x, 1 all over x squared plus 1, x all over x plus 2. And then later, after you start working with those in like pre-calculus, then they just throw these other ones in your lap. They're like, oh, here, by the way, here's e to the x. We don't really know what it is, but here's ln of x. Here's some trig for you, arc sine of x. And what I claim is that you can use, again, the idea of the limit to get from here to here. Okay? So again, the limit becomes a device to kind of tunnel from the things that we know currently to the things that we don't necessarily know all that well. Okay. And in particular, it's going to give us the ability to rewrite those functions, those functions over in this weird irrational land. We're going to be able to rewrite them as sort of polynomials, but sequences of polynomials. Okay. Okay. So let's see that. How can I get from one to the other? Well, you're going to be able to do sequences of polynomials. So instead of writing a1, a2, I'm going to write s1. So s1 I'll say is 1. s2 is going to be 1 plus x. Okay. S3 is going to be 1 plus x squared all over 2 factorial. S sub 4 is going to be 1 plus x cubed all over 2 factorial, sorry, x squared over 2 factorial plus x cubed all over 3 factorial, and then on and on and on. So hopefully you can appreciate that's very similar to what we did up here with sequences of rational numbers going to an irrational number. So I claim we're going to, in this chapter, we're going to do the same sort of thing. We're going to build a sequence, basically, of polynomials. And I claim if you take the limit of these things as we go to infinity, you're going to end up with one of these weird functions that you just kind of threw in your lap, and they seem to have nothing to do with what we're already learning. Okay? But it's because of that limit process. You needed calculus for this limit stuff. And so we couldn't kind of explain to you where they came from. We just sort of threw them in your lap. Oh, here you go. Here you are, buddy. You know? Okay? So that's in a nutshell, that's a lot of what Chapter 9 is trying to accomplish. We're trying to make this equivalence between e to the x and the sequence of polynomials, which basically ends up being an infinitely long polynomial when you take the limit. So it'll turn out that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, on and on and on and on. Okay. It's basically the limit of a bunch of polynomials, and that's what gives us e to the x. Okay, there's other issues involved, though. Okay, and the issue is sometimes you can have sequences of numbers that don't really even go anywhere. So you can have limits of rational numbers which kind of don't throw you anywhere. So they call these kind of limits divergent. Okay, the limits that go somewhere, you know, they can send you into irrational numbers. Of course, there can be limits that just go right back into the rationals. I don't want to claim that limits always go out of the rationals. Obviously, the sequence 1, 1, 1, 1, 1 will go to 1. That's a sequence of rational numbers that goes to a rational number, right? But what I do claim is that there are these weird limits that kind of don't work. Okay? And so you can imagine a sequence of rational numbers that don't go to irrationals and they don't go to rationals. So some sequences don't seem to work at all. It's kind of like dividing by 0, right? When you divide by 0, you don't get anywhere. You just are kind of lost. Some sequences or limits basically don't work, and we're going to call those divergent. So we call these divergent. If they do work, we call them convergent. You may remember that word from our work with improper integrals, right? So a sequence of rational numbers that doesn't seem to go anywhere would be something like 1, 3, 5, 7, 9. And then if you take the limit as we go to infinity, it doesn't really go anywhere. Let's pretend it goes to 1,000,000, right? Well, clearly I can find a place in the sequence where it goes to 1,000,001. Let's say the biggest number is 1,000,000,000. Well, you could clearly find a number in the sequence that's 1,000,000,001, something bigger. So as it goes to infinity, this thing just kind of goes out of the box. You know, it doesn't go anywhere in particular. It doesn't go to a rational. It doesn't go to irrational. Where does it go? I don't know. It goes out of the box. Okay. You can classify different kinds of divergence, and I think Ramanujan is kind of known for that. I'm not sure. I've never really studied it. I've seen some number file videos on it, but that's about it. Okay. But if you're interested, Ramanujan, I believe, studies divergence sequences, which we're not going to bother with. We're just going to kind of throw them in the trash and say, hey, these are worthless. I don't care. Okay. So in other words, for us to have a sequence of polynomials that we care about, it has to converge. And actually, the first 6 sections of Chapter 9 are working with that problem. Which sequences converge and which sequences diverge? Because if they diverge, we're not going to be able to use them in the first place. We're not going to be able to use them to make these kind of statements. E to the x is equal to something. We're not going to be able to use them to figure out numbers like e, right? We're not going to be able to produce these sequences that go somewhere, like this guy goes to e. Okay, so Chapter 9, I would say there's kind of 2 things. First, convergent versus divergent sequences, or limits. And that's just usefulness. These convergent sequences are useful. The divergent sequences are not useful. And then secondly, there's this idea of us being able to kind of re-envision all of these weirdly introduced functions. So re-visioning stuff like cosine x, ln x, e to the x as kind of polynomials or sequences of polynomials, and ultimately infinitely long polynomials. Okay, so revisions of cosine x, ln x, ex as sequences of polynomials, I'll say. And that will allow us to do things like integrate e to the x squared, which we can't do in terms of elementary functions, because now we're going to be able to rewrite it. Well, we note e to the x from above. I kind of let the cat out of the bag is equal to 1 plus 1 plus 1 all over x, x all over 2 plus x squared all over 2. So this would be, it's 1 plus x squared all over 2 plus x cubed all over 3 factorial plus x to the 4th over 4 factorial. So you could substitute x squared into this, and then just take the integral of this polynomial. And you can even take a little bit of the polynomial and it will become an approximation. Okay. Okay, so that's the 2 points of Chapter 9. This is basically sections 9.2 to 9.6. 9.7 to 9.10 is this stuff. Okay, and then 9.1 will introduce the idea of sequences along with limits. Okay, so I consider this not just Chapter 9, but it's more of a Chapter 9 kind of overview introduction. Okay. Okay, so for our quiz, our video quiz for this Chapter 9 introduction, So what are video lectures? Let's find what video lecture I'm on. Which video homework I'm on, sorry. So, looks like we just finished up number 4 and number 5. This will be the first question in homework, video homework number 6. Use your calculator to find what this number is. So 1 plus 1 plus 1 all over 2 plus 1 all over 3 factorial plus 1 all over 4 factorial plus 1 all over 5 factorial plus 1 over 6 factorial. Okay. And put that in your calculator and figure it out, and that will be the first quiz and video quiz homework. What did I say? Number 5? Or is that really number 6 or something? I guess number 6. Video homework section number 6. Let me write that down. I'm just remind myself. Homework 6. So 9. To call this 9.1 intro. Let's just call this chapter 9 intro. Okay, so chapter 9 intro. Use calculator to find 1 plus 1 plus 1/2 plus 1 over, and it should be close to the number e. Okay. So you can get me a fraction and a decimal, and you can use Wolfram Alpha like I do. Just plug it in there and figure out what it is. This answer in Wolfram Alpha is just up to 1 over 5 factorial, so I want you to go one more. Okay, thanks for watching. Hopefully this helps a little bit. I find chapter 9 is just really, really kind of out there in left field, but I think hopefully this will give you some scaffolding. I'm sure if you handed this off to Mr. Math over there at Harvard, they would probably be upset that I'm not being perfect with some of this stuff. You have to take a class and probably real analysis to really get the flavor of working with sequences of things. But I think this will give us some scaffolding and hopefully allow us to better understand or better sort of, kind of deal with chapter 9, because it really does seem out of left field. Okay, so thanks for watching, and we'll see you next time.